And yes, and yeah, we're really grateful to have you, and we're excited to hear today about supernova and or not, and about planets, and have some great discussion. So the format is our speakers will talk for about 20 minutes each, and then we'll have time for about 10 minutes of question and answer. And we'll try to finish at 12 o'clock. Yeah, so our first speaker today is Jennifer Andrews. Jennifer is a researcher at the University of Arizona. She is an expert on following all things transient in the night sky. But I think your specialty that has evolved has really become explosions where there is lots of other material around. So sort of these like bizarre luminous supernovae that we'll get to hear about today. But for this, you were a postdoc and in a couple places, and you did your PhD at LSU. And we're delighted to have you here today. Thank you for navigating the time difference and getting up early. I hope you weren't observing last night.
No, unfortunately, they won't let us on the mountains yet, but we're doing remote stuff.
Yes,
so
I see.
The Q observers are handling that right now.
Well, thank you so much.
Great. All right, let's share the screen then. All right. Yes, and like Morgan said, I am at University of Arizona, where I started as a postdoc with Nathan Smith. And as often happens, I think when everyone gets to Tucson, no one really wants to leave. And so we find reasons to stay around for as long as you can. And when working with Nathan Smith, you end up, whether you want to or not, working on Eta Car and massive stars and things that lose a lot of mass prior to ending their life. So let's see, I'm gonna put this where I'm not staring at it. There we go. Yeah, so today I'm just gonna talk about supernova. Let me start my timer so that I do not run over. About supernova imposters and the eruptions of massive stars. I am a complete observational astronomer, so theory is not in my wheelhouse, but I will gladly supply theorists with any observations they want. So to start off with, oh, are you not going to advance? Okay, I may have to click. Oh, now I can't see my title slide. There we go. So some of you may or may not have seen this plot by Monzi before, where we have absolute magnitude and timescale of various types of transients. These are, if you see, so absolute magnitude, so towards the top, we have our thermonuclear, and then our core collapse supernovae, and then down at the bottom, all kinds of interesting recurrent or novae and classical novae and all that sort of stuff. And then everywhere in between, say between -10, an absolute V magnitude of -10 to maybe -14 or 15, are kind of what we dub gap transients. And you can see a few examples. Well, 87A, not a gap transient, but it's on kind of the fainter end of the core collapse supernovae. And then the beautiful B838 Mon and Eta Car here in sort of the LBV region. So they're called sort of gap transients because they're in the gap between classical novae and core collapse supernovae. But they are often referred to as supernova imposters. They're sort of interchangeable, and depending on who you ask and what day it is, they can be sort of subdivided into 3 different categories. And you'll see this plot again so we can discuss which types of transients refer to what type of object. But sort of the very simple picture is that we can break down these gap transients, these supernova imposters, into sort of 3 camps, one being LBVs, so massive blue stars that variable. Usually these are the super Eddington eruptions, so the really big eruptions where they get brighter by more than a magnitude of, more than 1 or 2 magnitudes. These were kind of generally the first supernova imposters that were noticed, and So often supernova, imposter, and LBV is used interchangeably, but I'm trying to make the distinction here that they are different. And then you have the luminous red novae, which are generally, we think, merger candidates, merger events, common envelope events. And then finally, these intermediate luminosity red transients. I also call them 2008S-like because it's easier for me to remember which, instead of trying to figure out what the acronym means. And it's based on the 2008S was sort of the first object, the canonical object that we refer to. And we think these come from low mass electron capture supernovae. Now, as you can see on the bottom, these are optical spectra of these different events. And especially when they're first detected, as you can notice, if you are familiar at all with optical spectroscopy, is they look almost identical. So when you discover a transient, and you take the spectrum and you try to classify it, often, if we were to look at just the cross section here, we see these nice, strong, narrow Balmer lines, H alpha, sometimes H beta, occasionally some calcium lines, but early on they're almost indistinguishable. So often when these are discovered, they're just put out in an astronomer telegram or various other events as a interacting supernova or an LBV eruption, sort of the two camps they're put into. And not until we get additional spectra and light curves can we sort of figure out where they fit into the whole scheme of things, because as we'll see in a second, a lot of these also span a wide range of absolute magnitudes, so that even makes it harder without having an evolution with time figure out what's going on. So the major LBV eruptions, the first class, and what I'm going to kind of talk about the most is in this region here. So the time scale is how long it takes to decline one magnitude. And I think it's usually the R band. And so you can see LBVs can last a long time, and they sort of run the gamut in the full supernova imposter range. Like I said, they're from massive blue progenitors, the super Eddington eruptions. So the other event are the Esteratus eruptions that are sort of, 1 to 2 magnitudes. They're very small. The most important thing, I think, is that they survive the event. So the light curves, as you can see at the bottom corner here, it's Eta Car, P Cygni, quite a few LBVs having these massive eruptions. And you can see for thousands of days afterwards, it takes a while for it to fade. It can take a while for the LBV to fade. And it does survive the event. Eta Car is an example, it's still there. But once again, the spectra look like interacting supernovae. So it's hard to distinguish at first because you can see absolute magnitude wise, it kind of runs the whole gamut here. Now, the intermediate luminosity transients, the ILRTs, or the 2008S-like, and in fact, you can see a light curve of 2008S here. Like I said, we think these come from lower mass stars. They're super AGBs that have some electron capture that come from electron capture supernovae. And so they are terminal. There shouldn't be anything left. They're usually have dust enshrouded progenitors, so that you don't find the progenitor in the optical if you happen to have serendipitous imaging beforehand. You can usually find them in the IR, particularly if you have Spitzer imaging. Once again, their spectra look like interacting supernovae, but they fade quite quicker than the ILRTs. And just keep in mind where I say that they usually almost always have dust enshrouded progenitors, because that's sort of the whole crux of my talk today. And then finally, luminous red novae. They're brighter than red novae, and so they're called luminous red novae. We're very good at naming things. Generally, sort of, with the 838 Mon in particular, and then other mergers, they were kind of put in this lower magnitude regime, but we've been finding over the years that you can actually have luminous red novae that are quite bright. And like I said, we think they're mergers and or the common envelope ejection. They can be both low and high mass stars. One very distinct characteristic why you need to keep following these is their light curves generally have multiple peaks. And you can see down here, these are a couple, so B838 Mon has multiple peaks, but a couple of other objects, there's a red peak and, or first one peak and a two peaks, often called the blue and the red peak. And the peaks can be separated, which we think, and I'm not going to go into much here, but based on the masses of the stars. So that's a good predictor there that it's a merger event. So sort of what I want to focus on is, can some or all of these 2008 S-like, the intermediate ILRTs, could, instead of being these low mass AGB stars, can they be dusty, massive stars, but maybe with an interesting viewing angle? Or in other words, can some of the three different types of gap transients blur lines between? Can you have multiple types of, can you have an LBB be an ILRT? And the motivation for this is an object that we found in nearby, about 10 megaparsecs, M74. So you can see on the right, it's a beautiful Gemini image there. And it was actually an object that was discovered in Spitzer. So if you see down the bottom corner, the 2019 May 17, it was actually, it was discovered in July, and we scrounged back and went through the archives, and sure enough, it was actually detected both in Spitzer and in HST images. Interestingly, it was behind the sun in May, so we didn't catch it on the ground when it was bright in the optical, but thankfully Spitzer doesn't have to worry so much, or didn't have to worry so much about what us people from the ground could see, and was able to catch it earlier. So we think we got the maximum in the mid-IR here. But you can see that on the first panel is HST imaging in the I band. And you can see the progenitor in the top, and on the bottom, this is the detection after the eruption. And then in the middle panels are the Spitzer images here. But what's really interesting is that because M74 is a very well-studied galaxy, there's been at least 3 other supernovae in it that we know of. There was a ton of archival data. And so we poured through all of that and found not only archival HST data, but collaborators actually had a whole bunch of deep LBT data, so the large binocular telescope data. And we were able to reconstruct a light curve of the progenitor for over 6,000 days. So this is a combination of HST and LBT data. And the thing to kind of, the Spitzer light curve up at the top, those are mostly upper limits. It was right at the detection range. This thing is 10 megaparsecs away. It's, it's pretty far, and it's on the fainter end, so it's not a supernovae. But there doesn't seem to be any major outbursts from 2002 on. So this thing's been pretty stable. And then somewhere so this dashed line here indicates our May 17th Spitzer point. So we're just calling that the max, give or take a few weeks. Then it just brightened from quite a few magnitudes, as you can see here in the image, and then has started to decline. So it was really interesting that we had this fantastic data set. And as I mentioned before, these ILRT types of objects have never had progenitors seen in the optical. So we didn't immediately assume that it was that type of object. But then when we looked at the spectroscopy, it was very interesting. They show only like the Balmer lines, hydrogen here, and calcium lines, and nothing. It was fairly flat continuum. It seemed to indicate interaction because there's no P Cygni absorptions, anything like that. and here on the right is a subsample of these ILRTs. So there's 2008S here. And while it was classified as sort of a 2N or an interacting supernova or an LBV, you know, it could be other things. So we kept following it. And it does have characteristics that look quite like these 2008S objects. Interestingly, there was a serendipitous MVis VLT spectrum of the progenitor beforehand. So we actually have a progenitor spectra from a couple of months before explosion, which was really interesting and allowed us to see that not only with time has the hydrogen shape not changed much, but that there was already some sort of interesting physics going on with the progenitor there. But it also hardly changed with time. Okay, was that my 5-minute bell? Okay. And like I said, there was no outburst in the decade prior to eruption. And here are some examples of other types of ILRTs. These are sort of the mergers and LBVs. And so it could be plotting up against the light curves, it could be quite a few different types of objects. But this is, I think, really the interesting part. We plot up some CMDs here. So this is the HST 336 and 555 against the 336. And of course, these are not going to give us exact masses. These are, you know, single star models, but it gives us an idea of what the mass of the progenitor may be. And if we change the extinction, which we can't quite quantify because of multiple things, but one being if there's dust immediately around the object, it can destroy it while it gets brighter. It can also mask any of the normal lines we use to sort of measure what the extinction is. But basically, depending on how much extinction we apply, we can get masses ranging from 13 to 58. And the main picture to pull away here is that it's not a low mass star. This is a massive star, and it's blue. And because we had so much early time deep HST data of the progenitor, I thought it was really interesting that depending on at what epoch, so in the different color circles or different epochs, what epoch you actually observe and use to determine the mass, it gave you a slightly different mass and even sort of evolutionary state, which sort of cautions against using just one epoch, especially if you have only one or two color, to classify the mass of your object. But hey, we can only use what we have. So thankfully we had a embarrassment of riches and progenitor data for this guy. But sort of the final takeaway, I guess I might show the Eta Car video, is that this really looks like that it is a hot blue massive star that resembles a transient class that we think comes from low mass, very dusty electron capture supernovae types. So 2008S and NGC 300OT here, and the teal and the purple are the canonical members there. And while our object is much, much brighter in the optical, it's roughly the same brightness in the IR. And that led us to think, and that along with the morphology of the emission lines. So over here, this is the H alpha emission line. KRL is here in the black, and then here are some other 2008S like objects. So it's a little bit faster and it's got a kind of an interesting shape. But that led us to think that maybe what we're seeing is the same phenomenon, but from a different viewing angle. So if dust and the CSM is around the star, sort of in a disk or a torus, and we happen to look at it pole on instead of edge on, it'll be bright in both the optical and the infrared. If we happen to view this object from edge on, it would be obscured in the optical, but very bright in the IR. So you could have a bright optical and IR progenitor if you just happen to be looking, down the pole of this object. And to sort of summarize that, the different viewing angles, if you're looking through different columns of the same asymmetric CSM, it can look like you have two observational classes, but they're really the same phenomenon, just coming from the viewing angle that you are sort of looking at. So if you assume spherical symmetry, then you would think there were two different viewing classes, or two different types of observational classes, but in fact, they could be just coming from one event. And so I think, oh wait, do I still have time? Yes. What is AT 2019 KRL? So it could be a bunch of things, but these are the different sort of classes. And we don't know if it'll survive the event. So that's sort of the big thing. So of course, we need late time HST or large telescopes observations to see if it's there, particularly in the blue, because if it is an LBB eruption or a merger of some sort, it may have gotten hotter, but fainter in the red band. So we need some UV or U band images to see. So we aren't exactly sure what it is, but we think it is we know it is a massive blue star that mimics a 2008-like event. And the reason, sort of to tie this all together, because I can't, like I said, not talk about Eta Car, is, I'm going to skip through these. I was very ambitious. Is that recently Nathan and I, with a bunch of collaborators, have a paper out using the light echoes from Eta Car, where we make a conjecture that it can possibly come from a merger scenario. So down at the bottom corner is sort of the video of what we think one possibility could be, where it's a two-phase merger scenario, and that it starts out as a tertiary, and then there's a lot of mass transfer, there's merging, there's the homunculus nebula there, and that basically what happens is there's a lot of CSM interaction that's causing sort of the second bright part of the sustained peak, and this can be sort of mapped by our light echo spectra. So to sort of summarize, everything can be have a massive blue progenitor if you look hard enough. So it seems like all three observational classes can have these massive blue stars, or at least we're finding evidence of it. And that we think that another LBV eruption, supernova imposter eruption, could be explained by a merger as well. So I'm going to leave it on the video and leave it there.
Thank you.
Thank you. That was great. Thanks. Also, yeah, thanks for playing the movie. It was a lot of fun.
It's always fun. Yeah, exactly.
Yeah, I'm glad we got to it. But that's a pretty neat idea of like all of these being the same class of object, just seen at different viewing angles.
Right.
So
it's probably not that is exactly what's happening. They're all from the exact same, but we can think about that, maybe it isn't, there are other, ways to explain it. Yeah.
Yeah, but it's definitely, it's nice to having like tying things together into a physical picture. And so I was just wondering, are there predictions of sort of what the covering fraction of this circumstellar dust is? And does that sort of kind of back of the envelope calculation work out with the sort of number of these events we have in different categories? Do we have an expectation of how many we should be seeing at which viewing angle, and if the numbers work out roughly?
Yeah, so it's possible. The problem, of course, is we are, our sample is limited, and a lot of them are galactic. But if you do look at massive stars, a lot of them most of them are in some sort of multiple system. And in instances where we can actually map or look around, especially the high mass loss stars, it does often seem that the circumstellar material is some sort of asymmetric, whether it's bilobal, whether it's, CSM or a disk or a torus. So it's definitely, it fits. I haven't done the numbers yet to see what is happening. And the other side is that we're still observing, especially the group out of Ohio State, looking at those 2008 types of objects to make sure that they are completely gone. And an interesting thing is they do seem terminal. There doesn't seem to be anything left there. But also there is a ton of dust, right? So you can hide a lot there as well. It does seem sort of consistent that they are, that those were terminal events, which, maybe there's just two different ways you can get the same observational characteristic. But of course, it could also just be way more dust than we have in the object that we observed. Yeah.
So yeah, it sounds like it would be really helpful to have like larger samples as always. And Morgan had a question sort of along those lines of if LSST will be useful in this regard, where the depth and cadence will be sufficient for nearby transients like the 19K RL that you talked about in this here.
Yeah, I think so. Especially, you'll be able to, at least with the light curves, throw them up on the on that transient, on that map, and sort of see where they fall. Yeah, so I think LSST is going to be, super useful in that. Now, it's going to be mined out to then go and look for progenitors and map, what you can find based on the light curves. That's what everyone's figuring out right now, right? Like how to find the best, juiciest transients. But yeah, I think it'll be super helpful, and we'll probably really fill in this whole map here and find all sorts of very weird stuff. But yes, I think number-wise, it's really going to help us. Now we won't have Spitzer, but hopefully with I don't know exactly where we're going to be with JWST and LSST overlap at all, but used in tandem if possible, that would be very useful for this sort of thing. Yeah. That's
very exciting. Because one other question Morgan had was about the red massive progenitors. What kind of transients those would produce?
Which ones? Sorry,
the massive red stars.
Oh, the massive red stars. Right. So usually our massive red stars are core collapse supernovae. Those are
totally fair. With the idea that like maybe if all of these kind of like blue and blue-ish progenitors seem to produce this variety of transients, is there maybe a variety of transients coming from redder progenitors also?
Right.
Where do those show up in our phase space?
Well, those, yeah, like I said, those are generally our core collapse supernovae. So I think the biggest thing here is that with the very blue stars, there are two channels, that they're supermassive or that they're normal low mass binary mergers that turn out to end up looking blue. So they already have a whole bunch of weird circumstellar material and weird dynamics going on. And that sort of makes it hard to distinguish between, I guess, cause and effect. If the LBD is caused by a merger or if it's caused by its own massive blueness, I guess, yeah, if that helps. Generally the red ones, I guess this technically a super HEB star would be quite red. And then that's going to be the other end, the 2008S like electron capture supernovae. So, but I think in the end, if you're red, you end up being terminal. If you're blue, you have a chance of reviving yourself.
So just to end it on kind of a very early universe node and hopefully future with JWST. So these are all massive stars and will be luminous and hopefully very abundant in the early universe. And you showed us that these blue variables are sustained at these high luminosities for a long time. So presumably they will have a huge impact on their early, those early galaxies. So do you expect this, will they be detectable at redshifts or whatever, 10 or so?
Yeah, I believe so. Yeah, I mean, they're quite dusty. They've lost a lot of mass. Mass moves, or it moves away, cools off, then we see it in the IR. So yeah, these are quite big ionization and dust producing things. So pretty sure we will see them with JWST. I'm not a high Z person, so I'm not exactly sure how far back we can see them, but yes, of course, massive stars have a lot of, they may be small in number, but they are mighty in what they do to their surroundings.
Awesome.
Yeah, it might be difficult to see one at a time, but you know, a number of them could have a noticeable effect at redshift 10.
Yeah, so I think that's really important then to have this more physical pictures like Jen is deriving so that we can interpret those observations. So very exciting stuff. Thank you so much.
Wonderful, thank you.
Thanks
Well,
for having me.
Let's continue on to our second speaker, Diana Powell, who is completing her PhD at UC Santa Cruz. She's also a Ford Foundation Dissertation Year Fellow this year. And Diana is an expert really on, I think, how the chemistry and in the title microphysics of these environments around other stars, whether that's in planetary atmospheres or protoplanetary disks, really shape what we observe when we look at them. And we're really excited to have you today. And we're jealous of your background picture of Santa Cruz.
That's why I put it there.
And thank you so much.
Awesome, thanks, Morgan. So yeah, I'm Diana Powell, and I'm a graduate student at UC Santa Cruz. Santa Cruz finally looks like this picture again, so I thought I'd share it. And today I'm really excited to talk with you all about protoplanetary disks and substellar atmospheres. And in particular, I will be focusing on insights that we can gain from understanding these objects from the perspective of microphysics. And so for the purposes of this talk, microphysics will refer to the physics governing the evolution of small particles in the presence of gas. And so the key question behind all of my research is, what is the origin, evolution, and nature of planets? And so the picture of planet formation that has emerged looks more or less like this. So planets form in protoplanetary disks, either from the accretion of solids and gas or the gravitational collapse of material. So protoplanetary disks constitute the building blocks of planetary systems. Then once the protoplanetary disk dissipates, a young planetary system remains. And then as time progresses, the planetary system will evolve, planets will find relatively stable orbits, and the planetary atmospheres will also evolve. Okay, so this is the general picture. But what I really want to know is empirically, what is the answer to this question? And we're all very lucky to be alive at a time where we can actually observe each of these stages of planetary evolution. So we can observe protoplanetary disks undergoing active planet formation, like the PDS-70 system shown here in the top right, where you can see these 2 points that are thought to be giant planets undergoing accretion. We can also observe young planetary systems directly, like the HR8799 system shown in the bottom left. And finally, we now have observations of over 4,000 evolved exoplanets. So with all of this data, this is really the era to start actively connecting planet formation to planetary characterization. And in particular, a promising avenue forward is to connect the properties of exoplanet atmospheres to the properties of protoplanetary disks. And so when we look at observations of protoplanetary disks, we are looking at small dust grains and some different trace gas species. And these recent observations are really spectacularly radially resolved. So they're gorgeous and there's lots of information, but they are also often limited. And in particular, that's due to a lack of direct probes of the primary disk properties, such as the total mass in the system, and then some of the detailed properties of the solid and gaseous mass constituents. And so this is particularly in the midplane, the planet-forming regions of the disk. And then when we look at detailed observations of young and evolved planetary systems, we're often looking at their atmospheres. And similarly, these observations are hindered by opacity sources, such as clouds and hazes that can obscure planetary properties. So to make the connection between protoplanetary disks and planetary atmospheres, we need better physical models to interpret current and upcoming observations. And I will argue in this talk that microphysics will be a really important player in making this connection, and that microphysics may well be key to really understanding the origin, evolution, and nature of planets. Okay, so in this talk, I'll cover a lot of ground, but I'll start by talking about substellar atmospheres with a focus on clouds. And then I'll move on to discussing the total mass in protoplanetary disks. And finally, I'll spend the most time in detail bringing the previous two topics together through a discussion of the evolution of carbon monoxide in protoplanetary disks. Okay, so let's talk about clouds. So we all have some intuition about clouds from our familiarity with clouds on Earth. But clouds are important beyond Earth and are in fact the dominant opacity source in most planetary atmospheres. Clouds are important tracers of atmospheric physics, such as mixing and transport. Clouds regulate the planetary climate through regulating radiative transfer and chemistry. And clouds must be understood when determining atmospheric abundances. Also, often the clouds in an atmosphere are the only thing that we see. So it is therefore an absolute necessity that we understand clouds when we're interpreting planetary atmospheres. Okay, so given this, there's a lot that we can learn about planetary atmospheres through studies of clouds. So it makes sense to understand how clouds form and evolve from first principles. So on the right here, I'm showing an example of some of my calculations of cloud properties in planetary atmospheres. So I'm plotting the mass density of cloud particles as a function of particle size and atmospheric pressure. And here, each of the different colors indicates a different cloud species. And all of the properties of the cloud particles shown here, such as their particle size distributions and vertical extents in the atmosphere, are calculated from first principles through consideration of the microphysical processes that I've shown here on the left. So by studying clouds from first principles, I can demonstrate how the microphysical properties of clouds shape atmospheric observations. So on the top right, I'm showing the impact of the cloud particle size distribution on the observed spectra of an exoplanet. And so in this case, I'm looking at a model of hot Jupiter. And so in black, I'm showing a model transmission spectra for a hot Jupiter with our fully resolved cloud particle size distribution. And then on the same plot in blue, I'm showing the transmission spectra if we take an average cloud particle size for each cloud species and conserve the total cloud mass. And as you can see, both the amplitude and the shape of the transmission spectra changes between these two cases, really demonstrating that understanding the cloud particle size distribution is important when interpreting observed spectra. And by studying clouds this way, I also consider barriers to cloud formation beyond thermodynamics. And this allows me to predict which cloud species are likely to dominate the observed spectra. So on the bottom right here in black, I'm showing a different model transmission spectra for a hot Jupiter, where we include the opacity from all the cloud species that form. In gray, I'm showing what the transmission spectra would look like without any clouds. So you can already see how much of an impact clouds have in shaping observations. And then in the different colors, I'm showing what the spectra would look like if we only consider opacity from a particular cloud species. And so in this case, silicate clouds dominate the atmospheric opacity across a broad wavelength range. So in addition to impacting spectra, clouds may also serve as probes of planetary properties, such as the interior thermal structure. So here I'm showing emission opacities as a function of wavelength and atmospheric pressure for a planet with the same upper atmosphere structure, so temperature structure, but different internal thermal structures. And here the dotted white line indicates the location where the clouds become opaque. So for the high entropy planet with a hotter interior, clouds are opaque as high as 0.1 bar. But for a cooler interior, low entropy interior planet, the clouds are only opaque at around 10 bar. So clouds may thus be able to serve as probes of planetary interiors, as they are sensitive to planetary properties across different scales. And I've also shown that clouds are likely to enhance observed atmospheric inhomogeneity in certain cases in a way that should be clearly visible with James Webb. So here I'm showing 2-scale limb radii differences for a hot Jupiter in the case of clouds on the top and for a cloud-free atmosphere on the bottom. So you can look at these little teal slices to see that the cloudy atmosphere has distinctly asymmetrical limb radii. That is significantly, so these limbs are significantly more inhomogeneous than the clear atmosphere case, which also has limb asymmetry, but this is just due to temperature differences on this particular planet. And so we've worked to develop a tool for probing this atmospheric inhomogeneity relatively cheaply using James Webb. Okay. And finally, microphysical clouds can be used to explain existing observations. So here I'm showing the color magnitude diagram for brown dwarfs with the relatively recently discovered sequence of very low gravity brown dwarfs highlighted here in yellow. Okay, so the model very low gravity profiles with clear atmospheres lie in this region of the diagram where we did not really observe any brown dwarfs. And if we model clouds in these atmospheres without microphysics, then the points lie here. So they are much redder than the clear cases, which indicates that clouds are shaping these observations. But here they start to become more clear at lower equilibrium temperatures. Then when we instead consider microphysical clouds, those points lie here. And we can see a distinct shift towards the red region of the diagram, particularly for the cooler objects. And something that is particularly encouraging about the microphysical results here is that the points follow the straight slope of the sequence down to the reddest regions where we are currently discovering objects, instead of curving off to the blue. And so these results demonstrate that Binsky microphysical clouds naturally reproduce the very low gravity sequence of brown dwarfs. Okay, so we've discussed the importance of understanding clouds in substellar atmospheres, which is important in constraining evolved planets. And now for the remainder of this talk, let's turn our attention to protoplanetary disks, so the locations of planet formation. And I will start by talking about the interesting question of how much total mass is present in these systems. Okay, so the most common tracers of protoplanetary disk properties are dust or trace gases. And so I'll focus on CO gas. And these are relatively easy to observe. But due to a lack of the direct probe of the main mass constituent, which is H2 gas, previous measures of disk mass have relied on some tracer to H2 ratio. But we know that processes such as grain growth and drift, so when these dust particles grow and move aerodynamically, this should alter the dust to gas ratio from the typical ISM value. And several lines of evidence also suggest that gas phase CO, so particularly in the commonly observed upper disk layers, is depleted in disks. So this begs the questions: how can we measure the total disk mass without an assumed tracer to H2 ratio? And also, what is happening to all of the CO? And so we began addressing these questions by considering recent multi-wavelength observations of disks in the millimeter. So here I'm showing a visualization of observations put together by Sean Andrews at the disk TW Hydra. So here, these are all images of the same disk where it appears smaller in radius at longer wavelengths. And to introduce some terminology, I refer to the maximum radius in which emission at a particular wavelength cuts off as a dust line. And as others have suggested, these observations may be signatures of particle drift. So particles drift in disks because the gas feels an outward pressure gradient. So this causes there to be a drag on the particles. This drag removes the angular momentum from the particles and causes them to inspiral towards their host star. And so we can use these observations of particle drift to trace the aerodynamic properties of the observed particles and determine the total gas mass present in these systems. So we can do this following the simple equation shown here on the right if we know several key quantities. So in particular, if we know the maximum radius in which particles of a given size are present. And luckily, we can infer the particle size if the observed wavelength corresponds to the primary particle size contributing to the observed emission, particularly at the disk outer edge. And we can robustly measure the disk size to determine the radius in which these particles are the maximally sized grains. And this method is really nice because it allows us to derive the disk surface density without assuming a tracer to H2 ratio. And that's because we only care about how fast these particles drift, so their aerodynamic properties, which depends on their size and not how many particles are present. So in my recent paper, we've applied this model to 7 protoplanetary disks with previous millimeter observations that show decreasing disk radial extent with wavelength. And here I'm showing some of the observations for 3 out of the 7 disks in our sample. And so we can do a lot with this modeling, but one of the key things that we found is that disk masses are larger than we initially expected. So here on the left, I'm showing total gaseous surface densities in black for 2 of the disks in my sample. So that here, these black lines are the dust line derived surface densities. And I'm comparing the surface density to previous tracer derived surface densities and the minimum mass solar nebula. So the disks in our sample are 9 to 27% of their host stellar masses. And so this is significantly more massive than the minimum mass solar nebula. These disks are also 2 to 15 times more massive than estimates from optically thin dust emission, assuming an ISM dust to gas ratio. So also for the 3 disks in our sample with resolved CO emission, our estimates are 3, 40, and 115 times more massive than previously published. So we find that CO is depleted from expected values and that CO depletion is not uniform across different disks. So these results indicate that dust is a more robust tracer of total mass because we uncover a reduced gas to dust ratio that is roughly consistent across our sample, while the CO to H2 ratio varies more strongly. And I will come back to this in just a moment. Okay, so this work led me to this new picture of disks, where they may be more massive than previously appreciated. So in this picture, the total dust mass is about the same, but the total gas mass is an order of magnitude larger. And these qualitative changes to models of protoplanetary disks have significant implications for theories of planet formation. And that's particularly true for any process where the disk mass or the amount of gas affects the evolution of solids. Any process that relies on those will be affected by this picture. And so in my remaining time, I'll turn my attention to discussing CO and disks. So we've discussed the total mass, but really what's happening to all of the CO. And we really want to know the answer to this question because CO has been used as a tracer for a broad range of fundamental disk properties. And to answer this question, I will combine the 2 methods that I've used so far in this talk. So modeling clouds and modeling disks. And I'll just quickly step back and say that it's not just my modeling that indicates that CO is depleted in disks. So on the left here, I'm showing the CO abundance in the disk TW Hydra as a function of radius, as compared to the abundance that we would expect from observations of the interstellar medium. So you can see that CO gas appears to be significantly depleted. And the same is true if we look at large samples of disks. So here I'm showing an ALMA survey of disks in Lupus, where the disks span several orders of magnitude in dust mass, but have fairly constant gas masses estimated from CO. So in short, we observe much less CO in disks than we would expect or than would be predicted using previous disk models. And so to address this problem, I've coupled my model for protoplanetary disk properties with an adapted version of the models that I use to study cloud formation in planetary atmospheres. And in this context, I'm modeling the formation of ice on dust in disks. And what turns out to be particularly important in this modeling is that the nucleation and growth processes in the scheme include the Kelvin effect. So the Kelvin effect is a surface tension effect that quantifies the stability of particles through considering the strength of the molecular surface bonds. And I like to think about this in terms of geometry, where an ice molecule on the surface of a small grain will not be able to molecularly bond to as many neighbors as it would on a large particle. And so in short, the Kelvin effect causes large particles to nucleate and grow more easily. And so the particle sizes are important here because they regulate the level of depletion of gaseous CO. So if we approximate a disk temperature structure, as shown here on the left, where the disk is isothermal until it reaches a height where the surface layer heating is efficient. In the midplane, the disk is cold enough for ice to form on dust grains. So there will be a region of the disk where ice is stable, and then a region where evaporation could occur. So if the ice particles that form in the midplane are small, then they could be lofted to the upper regions and evaporate such that CO gas is not significantly depleted. On the other hand, if the ice particle is large, it can deplete the CO gas in the midplane. And so that's what I'm showing here on the right. So once the initial abundance of CO gas, shown in solid black, is depleted in the midplane, as shown in gray, there's a concentration gradient. So this gray line has quite gradient, which is then smoothed by vertical diffusion. And so this would ultimately lead to a depletion of CO in the observed upper levels, as shown in solid red. And this is the so-called cold finger effect, which can lead to a large depletion of CO gas in the upper disk. And so the particles and gas in the system evolve radially as well as vertically. And so at early times, gas is depleted fastest in the disk just a bit exterior to the midplane ice line, where the disk is cold and vertical gas diffusion is relatively fast. With time, CO gas is increasingly depleted in the outer disk as vertical diffusion has time to operate. And then in the inner disk interior to the midplane ice line, ice particles drift inwards until they reach a warm enough region of the inner disk where they release their volatile content. And this causes there to be an increased abundance of CO gas in the inner disk that can then be accreted onto the host star. Okay, bear with me through one pretty picture before I show you some final results. Okay, so I'll quickly walk you through the evolution of CO in disks. In the outer disk, CO gas is continually mixed down towards the disk midplane, where efficient ice formation occurs on large particles. These large particles drift inwards towards their host stars. Once these ice particles drift to the hotter regions of the disk, they release their volatile CO back into the gas phase. Some interesting cycling of material happens around the ice line. And then there's this enhanced abundance of CO gas in the inner disk that is accreted onto the host star over time. And so we find good agreement between our modeling results and observations. So I'm showing here the 4 disks that we model in plots B through E. And in our modeling, we find that this process depends strongly on diffusion, which contributes to the observed variance of CO depletion in different disks. So in the large plot here, you can see the amount of observed depletion in the outer disk depends on the amount of diffusion that has operated in the lifetime of these disks. And I will note that this process is also applicable to other volatiles in disks. So the microphysical processes of ice formation both regulates the observed abundances of CO gas and is crucial in determining the radial composition of protoplanetary disks. Okay, so I think my time is up. And so I'll conclude by saying that I've talked about understanding substellar atmospheres using cloud microphysics, and I've discussed uncovering fundamental properties of protoplanetary disks using particle aerodynamics and ice formation. And I hope I've shown and convinced you of the following concluding points. Thank you so much.
Thank you, Diana. This is really wonderful. So,
I really like the clapping track. That's nice.
yeah, I have to say this is, I first heard it at the Exoplanet presentation lounge, so I thought it was like really nice to kind of, yeah, show our appreciation. Like, thank you so much for.
Plus, we get to
doing this
pretend we're a
virtually.
sitcom, right?
So there are
You need
like
a
so
laugh
many.
track for that.
Yeah, in post-processing. I had so many questions as I noted down as you were going along, but maybe, and by the way, I love the illustrations. Maybe like just to you mentioned that this transition between like 4 and 5, and on this slide, on the I slide, that there is some interesting CO cycling happening there. So I was wondering, how important that transition is, and how can we go forward to understanding it, both, I guess, observationally and also on the theory side.
Yeah, so this wasn't a main focus of this work, although we do find what other people have found is that we confirm what other people have found with similar modeling, where when these ice particles drift in past the ice line, they release their gas. Some of that gas is then immediately cycled back. And that actually happens more efficiently in our modeling because we have this depleted gas exterior to the ice line that's quite significantly depleted. And so then it goes back across the ice line, forms more ice. Some of those ice particles drift in, but you end up with like an enhancement of ice just exterior to the ice line. And so people have proposed that that could be really important for forming planets. So people think that's a nice location to form giant planets. You have extra ice around. And then also observationally, so this has so far not been a favored model for the substructure we see in disks, but it has been proposed that ice lines could lead to the substructure that you see. Although I think that's a bit out of favor right now. People are mostly thinking planets, but it's good to have other alternatives.
Yes, it's good to keep an open mind. And sounds like Morgan has been thinking along the same line on this ice formation and CO depletion. And he's wondering whether this can teach us about the turbulent or accretion properties in the disks themselves.
Yeah, so something that's really nice in this modeling. So right now, so basically the main free parameter, the key free parameter I have for all of these systems is how much mixing is taking place. So I parameterize that diffusively like an alpha disk model. So very like bulk turbulent properties, but it is very sensitive to this parameter.
Is that like, is there vertical mixing? Because it seems like vertical mixing is important, but also the radial diffusion. Are they separate or are they linked by the same alpha kind of?
Yeah, so you could imagine them maybe like some process that could lead to anisotropic turbulence. So that's been proposed, I think, for different hydrodynamic instabilities. And our modeling, we assume that they're both linked by the same alpha.
Okay.
So the same alpha operating in both directions. So it's kind of like a bulk how much mixing is in these disks. But what's nice is that that's our free parameter. That's the one thing I tune in all of these plots. And for all of the disks, they lie in the range. The alphas that we get out are the kind of alphas you could plausibly expect to see in disks. So I don't get any crazy high alphas, crazy low alphas. So it seems reasonable. So I do think with more data, with more disks, actually really with more disks, I would feel comfortable saying that this is a nice probe of the turbulent properties, and then hopefully it could be ruled out or confirmed with some future observations.
And is the thought that that is I mean, maybe this is the case in the modeling, but also sort of in general, do we think that there should be an alpha that is constant within disk radius such that like the mass flux is preserved, or is that not the case in some of these disks because they have like maybe dead spots and stuff like that?
Yeah, I would say it's a very open question. You could definitely imagine. So something that could be kind of nice in this modeling. So right now we don't have great observations of the inner disk. Either it's optically thick or we don't have enough resolution. But you could imagine if there's lots of depletion in the inner disk, the way that you would get that from this model would be having increased mixing in the inner disk compared to the outer disk. There's some reasons to think that could be true. Like maybe you're driving MRI in the inner disk, you have dead zones in the outer disk. Maybe you accrete by disk winds, and that preferentially happens in the inner disk. So you could imagine there being quite a lot of structure to this alpha parameter, which we kind of smooth over and are just saying how much kind of bulk mixing do you need?
That's really interesting.
So maybe to close on on the topic of clouds. It was really nice to see all the different transmission spectra of clouds of different chemistries. And so I was wondering, like, will we be able to, actually determine the composition of clouds with JWST now that we have all of these nice predictions from your work?
Yeah, so I'm really excited about the prospects. So in particular, the kind of smoking gun for clouds are these broad absorption features in the infrared. You can see them in both of these plots here out past 10 microns. So they're kind of complicated. So they're broad, which makes them a little bit harder to detect. And also they depend sensitively on the size distribution. So you can see that in the top plot here. So you have basically the same cloud species, but the size distribution is different. And so the amplitude and shape of this looks different. But basically, if you get a broad feature there, then I think you're quite clear that it's particles blocking it. It's not something like high atmospheric mean molecular weight, which I didn't talk about. For giant planets, seems a little bit less likely. But if you do get like a nice, like in the bottom plot, you see this nice feature, definitely looks like silicate clouds. I think it's possible. There's also prospects of using them to probe atmospheric variability. Like if clouds are going through climate cycles and raining out, then you would expect that feature to maybe have significant amplitude variations, which is also exciting. So yeah, I think with James Webb, there's lots of awesome prospects, particularly for giant planets, but maybe even for small ones.
Excellent.
Well, definitely also.
Yeah. No, that would be really cool. I can imagine that. Yeah, that plays such a huge role on the chemistry of whole planets and habitability and so on. So yeah.
It's kind of amazing to start thinking about monitoring the weather on an exoplanet.
Yeah, it's
of course a little bit late,
today.
right? But
that's true. Just a few years delayed.
Excellent. Thank you so much. You'll have more questions for, I think, both of you on the Slack channel. So please stick around. Thank you all for joining us. CFA folks, we'll see you next week. And thanks to our speakers again.
thank you.
Thank you for having us.
For having me.
Well, thanks for coming. Okay, I can